Hi class, today we're going to start chapter 4, which is on exponential and logarithmic functions. So this is what the whole chapter is on, but today we are going to focus on section 4.1, exponential functions. So in chapter 3, we mostly looked at functions that were building blocks of polynomials or rational functions. So they looked like an x to the n all the way to a1x plus a naught. So these are our polynomials. So now we're going to start with a new building block function, which is an exponential. So it's something of the form, like for example, actually I want example to be yellow. Example. So if we look at 2 raised to the x, this is different than with our polynomials when we had an x raised to a number. Now we have 2 raised to the x. So functions like this, they grow faster than polynomials. So for example, if we have x squared and 2x and we plug in x equals 3, we will get 3 squared is 9, and then, oh wait, this is a silly example because this one is 2 to the third is 8, but then if we were to plug in x equals 5, we would get x squared is 25, and 2 to the fifth is 32. And if you keep going like that, you will see that the 2x will just keep getting bigger and bigger and bigger, where the x squared, it's still growing, but just not quite as quickly as 2 to the x. It will never catch back up to 2 to the x. Okay, so first I want to give some helpful tips in understanding how exponentials work. So helpful tips. So first, if a is a real number, we're actually going to look at it, a real number, a positive real number. So I'm just going to say if a is greater than 0, then, and also a real number, because with complex, we don't have a sense of greater than or less than. So a raised to the 0 power, this will equal 1 for any a. And then a to the first power, this will just equal itself, a. And then, yes, so, and if a is greater than 1, or it's actually like this. So if a is greater than 0, then a to the x is greater than 0 for all x. And the real numbers. So this little symbol here is n. And this symbol here is a fancy R for real numbers. It's just a little quicker for me to write this out than write all the words every time. And then if we have something like negative a, so it's going to look like this where you scale it by a negative, then this function negative a to the x, this will be less than 0 for all a, or for all x. All right, and notice that this is a strict inequality in both places. So if we have a to the x equals 0, only if a equals 0. Also, if we take 1 to the x, this equals 1 for all x. So these are just some helpful ideas on how to start getting familiar with how exponentials work. And now I'm going to give us how the graphs will look. So first, we're going to look at when a is greater than 1. So we'll take our, oh wow, I drew a line so bad even the tablet couldn't fix it. There we go. All right, that's a little better. So we're going to mark a 1 here and a 1 here. And so if we graph our function, it'll pass through 1 and then just keep getting bigger. And then right here, if we were to follow this up and then over, right here, this would be a. Because remember from above, if we have a to the first power, that just gives us a back out. And then if we have a less than 1, this will look like so again, we'll have our 1 and our 1. And then our graph will, it's kind of a reverse image of the other one. So here's our a. See, it's less than 1. So they're kind of this, they're the same image pretty much, except for they are flipped around the y-axis. All right, and then moving forward, we're going to look at how to identify graphs of exponentials, and then know the function from there. So how to identify graphs. So if given a graph, of a to the x and asked for a, so first we're going to start with an example. So if we have let me just draw the line first. So here, this is 1, and then if we were to if I was to give you the point 225, so we'll say that this over here is 25. All right, now since f of x, so f of 2 equals 25, this means that a squared equals 25. So therefore, f of x is 5 to the x. So you were given the x-axis, and we knew that the output needed to be 25. So then we solved backwards to solve for a. Similarly, if we were to look at another graph, but this time looking like this. Sorry, I know that my lines are getting a little squiggly there, but it's okay. Where this is 1. Then, if we were to look at a point like this, 3, 1/8, then, oh, and we'll call this graph g of x. So here, g of 3 equals 1/8. So this means that a cubed equals 1/8. Well, then we can see that not 1/3, 1/2 cubed, this will give us 1/8 since 2 cubed equals 8. So that lets us know that g of x will be 1/2 all raised to the x. And now this can also be written as 2 to the negative x. So a helpful fact is that if given a function where it's as a fraction 1 over q to the x, then we can rewrite as q to the negative x. So this is just helpful because sometimes if you don't like writing a fraction and you'd prefer just to have a negative sign, this is what it means. It's all right, and you do not need to write it like this. This is just if you prefer it. It's not required. So now we're going to talk about transformations of exponential functions. So we're going to look at how to transform their graphs. And I'll sometimes abbreviate exponential as EXP just because it's a lot faster to write, it's a little slower, and it's just nice and easy for me. So we are going to use 2x in these examples, but it could be for any positive real number, we could exchange that for 2. So, but we could use any positive real number and have a similar result. Okay, so first, we're going to look at external addition. So these should remind you of how we transformed graphs in chapter 3. It's all very similar, except this time our base graph is exponential instead of polynomial. So with external addition, let's take g of x equals 1 plus 2 to the x. So this will shift our graph up by 1. So if I graph some axes, and I'm actually going to just copy this axis because we're going to be drawing a good amount of graphs. Okay. So our normal graph would look something like this, where this is 2 to the x. But now we're shifting our graph up by 1. So that means our new graph will hug this asymptote here. This is 1 plus 2 to the x. So this will shift our horizontal asymptote. And it shifts the whole graph up. And then here, our domain, the numbers that we can plug into our function that makes sense would be all of the real numbers. And this can also be written as negative infinity to positive infinity, but it's often shorter to write this fancy R, so either one works. And then the range, the outputs of this function. So originally it was 0 to positive infinity, but now that we've shifted it up by 1, it's 1 to positive infinity. And notice how we do not include 1. It's a soft bracket there. That is because this graph will never actually reach 1. It just approaches it, but it never actually gets there. All right, so now we're going to move on to our second transformation, which is scaling by a constant. So first, I'm going to scale by a positive number 2. So if we look at the graph, k of x, I said 2, I meant 5. We're going to scale by 5 times our graph 2 of the x. So here, I'm still trying to learn how to paste with this a lot easier. Well, that put it all the way at the bottom, so maybe we're not gonna, let's not actually try pasting. I'll just draw new axes every time. I was hoping that would help, but alas. Why is my pen not working? Okay. Sorry, class, having a little trouble. All right, there's gonna be a strange space there. Don't know why, we're just gonna roll with it. So our original graph would look like this. And then our new graph is going to be stretched up like this. So where this was 1, this is now 5. So our original graph, so if we were to plug in 0, we would have 5 times 1. So this is why our new y-intercept is 1. So this stretches our graph. All right, so our domain is still all of R. We can still plug in every number, but our range, it's also the same. It is 0 to infinity. Again, not including 0 because they never actually reach 0. All right, and now we're going to look at another example is if h of x is negative 2 to the x. Okay, and note that this means negative 2 to the x like this, not negative 2 raised to the x. So this will be the graph that we're working with for this section. All right, so this will flip our graph. So if we take our axes, our original graph will look like this, whereas our new graph will look like this. So this is negative 2 to the x, and this is positive 2 to the x. So this will flip across x-axis. So our domain remains the same. It is still all of the real numbers, but our range is now negative infinity to 0, because all of our outputs are going to be negative now. All right, and we'll have one last transformation that we'll use regularly, which is internal addition. So here we're going to look at t to the x equals 2x minus 1. So this is similar to chapter 3 where it shifts our graph left or right. So in this case, we will have our original graph, and it gets shifted to the right by 1. So now our graph will look something like this. So this is 2 to the x minus 1, and this is just 2 to the x. So this is, since we subtracted a number, that shifts it to the right. If we were to have added a number, it would have shifted the graph to the left. So our domain is all of the real numbers, and our range is still 0 to infinity. Okay, so now we're going to move on to the next section. Sorry, my pages are sticking together. Okay. Now we're going to look at something that is useful with exponential functions, and that is an application with compound interest. So compound interest is calculated by the following formula. So it's a to the t equals p times 1 plus r over n, all raised to the n times t power. So, and this is where a of t is the amount after t years. P is the principal, or the original amount. We'll mostly be talking about money and word problems, so it's usually the original amount of money. All right, and then R is the interest rate per year. And N is the number of years, or number of times, sorry. Interest is compounded per year. And this means the number of times in a year that, like, normally a bank would add your interest in. And T is the number of years. So this is a very important formula that we're going to be using for a lot of chapter 4. It'll definitely be on homework and midterms, so make sure you have this written down and you know how to use this well. So we're going to do an example. So a sum of $1,000 is invested at an interest rate of 12% per year. Find the amounts in the account after 4 years if interest is compounded annually, which means 1 time per year, semi-annually, which means 2 times per year, quarterly, which is 4 times a year, monthly, which is, whoops, forgot an L, which is pretty obviously 12 times a year, or daily, which is 365 times a year. So first, let's look at this word problem and figure out all of the parts that we need. So this $1,000, this is our principal, so this is our P. is invested at an interest rate of 12% a year. This 12%, this is our rate. And then 4 years, that is our T. And then these here, the interest annually, semi-annually, quarterly, monthly, or daily, that will give us our N. So I'm going to make a little table where we have our N and then the amount. So we're going to start with 1, 2, 4, 12, and 365. So using our formula, it will be 1,000 times 1 plus 12%, so 0.12, over 1 times 1 times 4. So here we have our principal of P, our 1, and then our 12% over the amount that we compound yearly, which is 1. And then again, that N, which is 1, and then times 4 years. And if you were to plug this into a calculator, you would get 1573.52. And then for semi-annually, it would be 1,000. 1 plus 0.12 over 2 times 2 times 4, all raised to the 2 times 4. So this is 1593.85. Then 1,000, 1 plus 0.12 over 4 to the 4 times 4 power. And this is 1604.71. And 1,001 plus 0.12, you kind of see the pattern here. Oh, whoops, not 4. 12. Whoa, click the wrong button. 12 times 4, and this will equal 1612.23. And then finally, 1,001 plus 0.12 over 365. And then 365 times 4, and this is 1615.95. So as you can see, it is better to have interest compounded more frequently. You end up with more money after 4 years versus if they compound it just once. There's a big difference here. Okay. So then if an investment earns compound interest then the annual percentage yield, also abbreviated as APY, is the simple interest rate that yields the same amount at the end, of 1 year. So in our final example, we're going to kind of look at what this means. So if we want to find the APY for an investment, that earns at a rate 6% per year, compounded daily, we would have, so this time we're just looking at 1 year, so we just would have the amount. It does not matter what the original principal is because we're just looking at the percentage for anything over the year. And it would be 1 plus 0.06 over 365 times 365. So here our t is 1, so we don't have it. There's like a secret 1 here, which is why we don't have it. All right, so this will then become p of 1.0618. So the annual percentage rate is that 1.06183. Okay, so on homework, you can use a calculator for these problems because they're kind of messy, and I understand that, and it would be impossible to do this in your head. I couldn't do it in my head. So, but on the midterm, we don't allow calculators at Cal Poly on pre-calc exams. So I will write it so that you will write it in like a simplest form on the midterm, but for the homework, you can use a calculator. Oops, it's not a Y. But not an exam. All right, so that's the end of this section. So I will record your section 4.2 video very soon. All right, have a great day.